Okay, so I've already talked to you guys about biosafety levels and things of that nature with the first lecture over Chapter 9, starting us off, and some of the common usages and why we use antimicrobials. So now we're going to get into the physical methods of microbial control. So I like to break this into two main groups. The first group we're going to look at are the physical methods. The next group is going to be the chemical methods. So when we're talking about physical methods, it's things such as heat, freezing, radiation, osmotic pressure, drying, things of that nature are going to be physical. Things that are going to be chemical are a lot of our disinfectants, things of that nature that we may use, and we're going to learn a little bit more about those as well as we go along. So let's go ahead and get started and talk about heat. That is our first physical method. Let me just go ahead and put physical methods. When we're looking at heat, we need to make sure we understand these terms. We have what's called thermal death point and thermal death time. So if you haven't gone to the physical methods of microbial control yet in your textbook, I'll go ahead and tell you where it is. It's on page 268 of your textbook, where it starts talking about physical methods of microbial control. And we start discussing thermal death point and thermal death time on the following page, page 269, excuse me. Thermal death point is the lowest temperature that kills all cells in a broth in 10 minutes. So let's look at that definition. Don't know how well you can see it. Hopefully you can see it okay. But thermal death point is the lowest temperature that kills all cells in a broth in 10 minutes. So it is the point or temperature in which all cells will die, microbes that we're trying to kill, in a set time. Okay, so the time doesn't change. However, thermal death time is going to be the exact opposite. It is the time it takes to sterilize or kill all cells in a particular volume of liquid at a set temperature. So the temperature will stay the same. Is the time it takes to sterilize a particular volume of liquid at a set temperature. The temperature will stay the same, and the time may fluctuate depending upon the species we're trying to kill. All species are different, and they're very special in the temperatures that they may prefer and the length and the time duration if we are not altering that temperature. So those are important things to consider and to evaluate when we are looking at an antimicrobial's effectiveness and their what we call efficacy, how efficient they are. Now, you've noticed when you look at an antimicrobial, and I'm sure a lot of you have been looking at disinfectants quite differently here lately, and you may have noticed that none of them say kills 100% of microorganisms. So what we like to evaluate here is decimal reduction time. This is the time required to destroy 90% of microbes in a sample. If you can get something that will effectively kill 90% of all microbes in a sample in a reasonable length of time, you have a fairly effective disinfectant. So that's something to consider, because we know it's very hard to destroy all pathogens and all microbes. However, sanitization, we can reduce the numbers to create a more what we call static environment that's going to be more conducive for, or less conducive for them to live and more conducive for us. I don't think I went through those terms earlier. And I don't know if it's in this textbook, in this chapter. But I do want to go ahead and mention it before we get into focusing on our methods. When we look at an agent, antimicrobial, we want to look at its effectiveness. So these terms are very important because you may see or something that says it's bactericidal or fungicidal or virucidal. If something ends in a CIDE, that means to kill. So if it's virucidal, it kills viruses. If it's bactericidal, it kills bacteria. Now, there is another term a little different. Static. If it ends in static, that means it reduces the numbers. Okay? So there are some things that are bacteriostatic. That means they reduce the number of bacteria. The fungistatic reduces the number of fungus. Virustatic reduces the number of viruses. Sometimes you may hear something called a microbicide or microbiostatic. This means that we reduce the number of microbes. This means we kill the number of most of our microbes. So these are also terms that are used commonly. We need to make sure we understand the difference between the two of these. Okay, so now we can officially get into our physical methods. Let me just, okay. And say heat. Okay. When we think of heat, we probably think of the summer and how hot it can get in Texas. However, there's various types of heat. We're going to start off with the first type. The first type is moist heat. We use moist heat a lot when we are looking at an effective way of reducing numbers of pathogens and things of that nature. There's a good number of reasons why we would use moist heat rather than dry heat. Now, water is more effective at conducting heat. It holds it. So therefore, we can kill pathogens at a lower set temperature using moisture. So that's one of our really good ways to be able to reduce the number of pathogens. So the first one we want to consider is boiling. This is a form of moist heat. Now, sometimes when you think boiling, you think, oh yeah, we've got this. We boil something, we're safe. It is not sterilization. So many people think that boiling is sterilization. It is not. Boiling is going to reduce the number of bacteria and fungus. It kills the what we call vegetative cells. Now, a lot of people don't understand what vegetative means. That these means the ones that are currently reproductive and growing. Okay? That means that it's not going to kill anything that can lie dormant. All right, a vegetative cell, the same term. Germinating. You hear them called a number of different things. They are meaning that they are capable of growing and reproducing at that time. So they're actually active. A dormant cell, remember when we talked about spores and things of that nature, those are your dormant ones. A vegetative cell is what we're going to be able to kill with moist heat. Therefore, this is not sterilization. Sterilization kills all microbes. So it's going to kill even the ones that are lying dormant, that are spores. So this is a very important thing to evaluate. So it kills vegetative cells of bacteria and fungus, certain types of protozoa, and most viruses. Not all viruses, we notice. Okay? How long do you have to boil? 10 minutes at sea level. When you change atmospheric pressure, it changes the length of time you have to do things. Okay, so it's important to realize the higher elevations, water boils at lower temperatures because atmospheric pressure is lower. Therefore, a longer boiling time is required in a higher atmospheric pressure such as Denver than in Los Angeles to get the same antimicrobial effects. So I don't know if you've ever noticed, but on the back of baking products, they will state if you are in a higher climate, higher atmospheric level, you need to have this length of time for cooking whatever. Why? Because, like we just said, the atmospheric pressure is lower, therefore the longer boiling times required. So, again, this is not sterilization. It is sanitization. Because if it's not one, it has to be the other. Okay? And when we sanitize, we know we're just reducing the numbers and we are not getting rid of everything. So we are not going to get rid of bacterial endospores, protozoan cysts, and certain viruses. Examples of those viruses would be such as hepatitis. You don't kill hepatitis when you boil water. Okay, so let's go to our next moist heat. Our next one is the autoclave. This one is going to use what we call pressurized steam. I love autoclaving. Autoclaving is what we use in a lot of our medical field. Every hospital is probably going to have an autoclave. So some of you have already been working with autoclaves. Now, they will go through and they will put linens, things of that nature, anything that can handle moisture will go into an autoclave. They seal the door, and then they're going to allow that pressure chamber to build up pressure with the steam, cycle through, and then after 15 minutes, ideally, it should be good. You'll notice on page 270, there's a picture of an autoclave. Let's go ahead and take a look at that. There's the actual autoclave. Now, you wouldn't look at it and see it like that. It would look more like this. Now, this is a tiny one that we're showing here. The ones in the hospitals are huge. They're in most medical laboratory and laboratory situations, you're going to have one that's at least 5-6 foot tall and about 3 to 4 foot in width. that you can compare this to. So there's your autoclave, and this is what it looks like on the inside. So here's your materials, whatever you put into the autoclave. So you've opened up this chamber here, the vault, if you will, and then placed your items in here. And then there's literally steam that's going to come through here and cycle. And it's going to come through, cycle for the length of time that we are required. And then it basically shuts off. And then you can open up your vault, okay, the chamber, and get your items out. Now, let's look at what the amounts are. This is a form of sterilization, by the way. And where is it? So I can just make sure. And I'm sure most of you that have been in the medical field at all have already seen one. Some of you may have had to go to the hospital for some reason, and you were just mesmerized by the wonderfully warm blankets that they would bring out and want them to come out with those immediately. Well, those are your blankets that have been fresh out of the autoclave. This we have to sterilize from one patient to the next. So know these numbers. It uses 15 pounds of pressure. So that's PSI. For 15 minutes at 121 degrees Celsius. Honestly, that's not a lot of time to be able to sterilize an item. It's very effective, very quick. And the problem is, though, a lot of oils, metals, things of that nature are not going to be able to be used or placed into an autoclave because we don't want to dull sharp objects, and of course oils and water don't mix, so that won't work either. So there's another number of problems that we have with using an autoclave in certain situations, and we'll get to what we use for that. The next form of moist heat is pasteurization. I kept telling you guys I was going to get back to pasteurization and go into it in more depth. Well, here we are with pasteurization. Pasteurization, we know who developed it, Louis Pasteur. It's a method of heating beer and wine just enough to destroy the microorganisms that cause spoilage without ruining the taste. We use pasteurization for a number of things nowadays. To kill pathogens in milk, ice cream, yogurt, fruit juices, things of that nature. And it's very effective for that. Pasteurization is not a form of sterilization. It is a form of sanitization. Sanitization. I can't spell today. Now, there's a number of different types of pasteurization. We have what's called the batch method, which is our most common method. Batch method, they take these great big huge tanks. If anybody's ever seen the dairy industry and seen pictures of these great big huge stainless steel tanks. I was trying to see if they had any pictures of it here. They don't. They're huge. They're massive. And they will literally take these and run them through what we call a batch method. 30 minutes at 63 degrees Celsius, I should say. Sorry. Okay. That one is the one that most milk processors today use, is high temperature short time pasteurization. This one is also known as flash pasteurization. Batch method is the oldest one known. Flash pasteurization, 72 degrees Celsius for 15 seconds. We also have ultra high pasteurization. I'm just going to do that abbreviation. And this one is going to heat it to 135 degrees Celsius for 1 second. We also have ultra high temperature sterilization. This one is used in a few situations. 140 degrees Celsius for 1 to 3 seconds. Then you want to do a rapid cool on that. Packages dairy creamer, those little packages they serve in the stores or that you can buy, those they use this, the ultra high temperature sterilization, so you can leave them out for long periods of time because of that. Because you notice how you can leave those little packages of creamer, and you may have thought, hey, why can we leave these little packages of creamer out, but we can't leave out a big bottle of milk or a big bottle of creamer? Why is it going to go bad so fast? Well, that's because these are going through the ultra high temperature sterilization process, and they will be good to leave out for a much longer length of time. I'm not saying indefinite, but much longer length of time. So the next one we want to look at is dry heat. So let me flip my paper over here. And we will go into dry heat and evaluate the difference between dry heat and moist heat. We're still on heat, but now we have dry heat. It's totally different heat than moist heat. So there's some substances, powders, oils, things of that nature. If they come in contact with liquid, it's going to ruin them. So we can't use boiling or steam methods to be able to sanitize our powders or our oils. We have to use things such as dry heat, also metal objects, like I said before. These are going to be damaged by exposure to steam, so we have to use dry heat. Dry heat is most commonly going to be using an oven, and it's honestly effective sterilizing agent. Okay, but let's look at the difference. 15 minutes, 15 pounds of pressure, 121 degrees Celsius. That's your autoclave. Now, an oven, to be just as effective at 121 degrees, it would take it 16 hours to sterilize. So, what do we do here? We got to turn the heat up. Have you ever noticed that it might be 85 in Texas, but that would be equivalent to probably 100 degrees in Arizona? Why? Because they have a dry heat versus our moist heat. All right, so 171 degrees Celsius for 1 hour. Or we may also use 160 degrees Celsius for 2 hours. And these are going to be effective at sterilizing your objects. However, what are some things we can't put in an oven at these temperatures? Think about how hot this is. Anything made of rubber, any plastics, paper. I don't think you want to put paper in your oven. Things of that nature cannot work very well and still cannot be sterilized in dry heat. Now let's look at the other form of dry heat that is the ultimate means of sterilization. And you've used this in class whenever we use the Bunsen burner. It's called incineration. Now let me make sure I spell this right, because I always spell it wrong for some reason. Incineration. Because I'm sitting here talking and writing is never... Multitasking can never always get you in trouble if you're not careful. Alright, so incineration is the ultimate means of sterilization. Incineration literally means to burn to ash. So what did we do that was incinerating? Well, we took our inoculating loops and we would run them through the flame back and forth until they reached a proper heat. So remember I said wait until they turn red? When they turn red, that means that they are properly sterilized. When they glow red, when metal glows red, it is 1500 degrees Celsius. That means you have burned everything to ash. A lot of times when we have questionable materials that we aren't sure about, we may burn the bandages and things of that nature, especially if you're out in the field. Paper cups, bags. Field microbiologists will incinerate carcasses of animals that may have certain diseases, anthrax disease, things of that nature. Now, some of you may remember the scare in the late 80s or so that was bovine spongiform encephalopathy, also known as mad cow disease. Nobody was really clear on the disease. Everything was new. And the only thing they felt confident in doing was to literally burn the bodies to ash. So they were burning thousands upon thousands of cattle. Also during the Black Plague, in the 1300s, not the 1300s, 13th century, 1400s, they would literally take bodies out, pile them up, and burn them. So incineration is a very effective means of sterilization, and if we don't have anything else, it can be useful. Ebola. We had the Ebola scare a couple of years ago, and we were trying to address what to do with the bodies. And the question did arise, should we burn them? Well, nowadays we're starting to come up with an understanding that when we do burn things, chemicals can be exposed in the air. So the one thing they were concerned about with the Ebola virus is if we do burn the body, which again, they were still unsure of, could it release the toxins of the Ebola virus into the air and the atmosphere? Because they weren't really sure. There was a lot of things they were really worried about because the toxins themselves from the Ebola virus, and how easily it was to become infected with it, they were concerned for, and they weren't 100% sure as to how to handle it. So if you followed much of that, they decided not to do the incineration, and instead they did some other means. But incineration is still considered the ultimate form of sterilization. However, it's just interesting how we're starting to look at it in a different light as we evolve. So I'm trying to chunk this into parts that's not going to be too overwhelming for you guys. And this is your heat section. I'm going to go ahead and stop, and then I'll go through the rest of the section because honestly heat is the longest one. And then the rest of it should be, the rest of the physical methods I should be able to do in one section.